This conference will now be recorded.
Okay, all right, so Friday we had kind of started talking about the life cycle of lymphocytes. And one big component of that, right, was trying to make sure that any lymphocyte that we essentially release into the wild is going to meet two basic criteria. Right? It's going to be immunocompetent, which is to say it can bind to an MHC receptor protein. It can do the job that we're asking it to do. And then the other half of it is that once bound to that MHC, it won't have a response or a reaction to a self-antigen. They are self-tolerant. Either of those two tests being failed are bad. Right? They fail the first one, they're just useless. Right? And if they fail the second one, we're going to have an autoimmune response, which again is not really something we're looking for. Right? So we need to have a safe place, a safe space maybe, for these lymphocytes to be tested, right? To see if they meet both of these criteria, so that if they fail one or both of them, then they can be eliminated without causing any problems. For T cells, this safe place for education for maturation, that's the technical term for the process, is in the thymus. And again, they're going to be under those two different tests, one under positive selection and one under negative selection. The positive selection here, right, is can you recognize a self-MHC? Right? If you can't, then you get destroyed. The other test here, the negative selection test, is making sure that you don't react against a self-antigen. You are self-tolerant. Again, if you fail that, you get destroyed. Simple as that. So the process essentially looks like this, if you want to think about it kind of a cartoon way of putting it. Here we have our T cell, right here in blue. Here we have our APC, right, our antigen presenting cell. And again, if you recall from last time, right, all of the antigens are in these MHC proteins. So basically, it's a little slot that we put an antigen in. Okay. This first test simply makes sure that the T cell receptor will line up, will match up with an MHC. Right. So here in the top one, the two shapes don't match, and so they don't. Right. So this cell would be destroyed. The bottom version, the cartoon here, right? The shapes match up. We bind, we mate. Okay, and so we're good to go and move on to the next test. The next test here, the negative selection version of it, right, is we had better not have a reaction. Now, the cartoon that we've got here is, but the way that's representing this here in the cartoon is whether or not this whole space is filled, right, by this antigen or not. So in this case, the antigen makes contact with the T cell. This is something that is not what we want. We're having a reaction here at this point. So again, this cell would be destroyed. This cell here, we're not having a reaction, and so we pass on. We pass both tests, and then we can be released for seeding. For B cells, right, we don't have a specialized structure for the maturation of B cells. It happens in the bone marrow. We have both tests, both basic kinds of tests here again, right? Although the selection is slightly different. So the positive selection, the way that we test if a B cell is immunocompetent, right, is can they produce a receptor for an antigen? Can they make a MHC? Okay. If they can, then we move on to the next step. If they can't produce that one, it's actually kind of antibody, believe it or not. They can't do that, then they don't get moved on. They move on to the, the negative selection part. The negative selection part is essentially identical to what we see with the T cells. We need to make sure that we're not self-reactive. So any B cell that is self-reactive gets destroyed. Anyone that is not self-reactive gets moved out and is allowed to seed into the lymph nodes. So at this point, right, we have our B cells and our T cells. They've been educated. They have their degree, so to speak, right? They've marched down the aisle and gotten their sheepskin and on, right? But they have no practical experience. They are naive, right? They are just like a recent college graduate. They have no work experience. So they have to go out and get that work experience. So what we're doing here is we're sending out these naive, and that is the technical term for this, these naive B cells and T cells out into the body. Right? We know that they're capable. We know that they're safe. So we let them out and go out and do what they're going to do. T cells will circulate throughout the body. B cells will find themselves in a follicle of some description, usually in a lymph node, but not necessarily have to be. Okay? It can also end up in the spleen, right, in that red pulp. It can be lots of different places. And there they are going to sit. They are going to sit there and wait. Because they haven't really got a job to do yet. They're not going to have a job. They're not going to transition from naive to, I guess, fully mature until they actually encounter a foreign antigen. And that's going to be the next stage in here. Right? Antigen encounter and activation. So they've trained for this their whole lives, right? And finally it happens. They encounter an APC, brings them an antigen from a foreign thing, and now, holy cats, we actually get to do what we're going to do. Okay? At this point, right, the lymphocyte is going to begin a process by which they make clones of themselves, okay, and have a very specific sort of reaction to that particular antibody or antigen. And this is the process of proliferation and diversification or differentiation. Okay. Once activated, we make a whole lot of copies of that cell. And the two different kinds of copies that we're going to get are going to be memory cells and effector cells. So an effector cell is going to be a lymphocyte that has some kind of activity. So if it's a cytotoxic T cell, that effector cell goes out and attacks those things. If it's a B cell, it's going to make antibodies against that particular thing. They're doing the job. The other clones, and there's a handful of these for every bunch of the others that we make, are going to be these memory cells. And so when we talk about the adaptive immune system having a memory, being able to have a stronger second or third or fourth or fifth reaction, the memory cells are what enable us to do that. Because these memory cells, basically, it's sort of like a saved game, right? You don't have to go through all of this process the next time around, right? You've already started, you're going to start on level 3 or whatever, right? And the next time this particular pathogen comes around, you've got the lymphocytes ready to go already on top of it. Now, your immune system and the ability of your immune system to fight off infection is largely genetic. And remember that all of these things are proteins, right? And you can only make the proteins that you have genes for. And so this is why things like novel diseases are such a big problem. When white Europeans came to North America and to South America, they brought with, and to Central America, they brought with them all kinds of diseases, right, that had been in Europe for hundreds or thousands of years, right? Long enough that those diseases essentially killed everybody who couldn't have an immune response to it. So everybody in Europe, right, was, it still killed people, but it wasn't quite the tragedy. Things like smallpox, things like bubonic plague, things that the people that were still there had their lineages had survived them. When they came to the Americas, those diseases had never been here before. And so they wiped out Native American populations because they physically could not mount an immune response against them. They were genetically incapable of doing that, right? And those few that survived it eventually did pass on that immunity to future generations, right? But, right, it was a big death toll early on. It's again the same reason that this particular coronavirus is so deadly, whereas other coronaviruses like the common cold are not. The common cold has been around, right? We have generally in the population have a capacity to respond to the common cold. We don't have a way to respond to COVID-19. So that's a big part of why this was a big deal, why swine flu was a big deal, why the bird flu was a big deal, why the flu of 1918 was a big deal, right? Why the bubonic plague was a big deal, all those sorts of things, because they were novel. Right? They weren't something that we had a genetic predisposition to be able to fight off. Antigen presenting cells, or APCs, right? Again, we mentioned early on in this particular part of the chapter that these are really important. Right? They are not the ones that are going to get all the glory. They're not B cells or T cells. Well, actually, sometimes they are. But these are the ones that make the whole thing happen. Right? These are the ones that are going to kickstart the adaptive immune reaction. Right? And so some of these are going to be things from the innate immune system. So dendritic cells play a big role in this. Macrophages play a big role in this. Right? Parts of that innate immune system. And perhaps confusingly here, but for reasons that we'll make clear as we move forward, B cells can also act as APCs. And they play a pretty good role, or play a pretty important role in the activation of lymphocytes. The idea here is that we're going to basically engulf, right, or somehow otherwise acquire the antigen from a pathogen. We're going to take that pathogen and we're going to put it in an MHC, and we're going to bring it over to a T cell and say, hey, look at this. This is kind of weird, right? Should we do something about this? These first two cell types, right, are typically what we expect to find. They're phagocytic, right? Dendritic cells, macrophages are both phagocytic. And so they're actively going out and finding or acquiring these antigens directly from the source. They are taking essentially everything, right, and then kind of dissolving everything but the antigen, or at least the antigenic determinant, and taking that to a T cell. And these are really, really useful in terms of activating T cells. Right? In terms of making them into the activated cells, this is really the biggest way that happens. And so, again, we talk a lot about the idea that there's a link or a connection between innate and adaptive immune systems. This is one of those links where the innate immune system feeds back on the adaptive. See a lot of examples of the adaptive kind of circling back and turning up the innate. Here we have the innate coming back and actually providing for some of the activity of the adaptive immune system. And so again, just to kind of give you a sense for this, it looks like this is a dendritic cell, so named because it has all of these branches, right, or dendrites on them. B lymphocytes are APCs also, or can be APCs also, but they are not going to be involved in the activation of T cells. What B lymphocytes are going to do is they are going to activate themselves with the help of a helper T cell. So while they will take the antigen to a T cell, okay, they have to take it to an already active T cell that will help activate the B cell itself. So they kind of almost activate themselves, I guess is the best way to think about it. A naive B cell is kind of its own APC. So to this point, right, we have this set of lots of different kinds of cells. Right? We have B cells and T cells, we have APCs, and we have antigens, right, carried in our MHCs. And crucially, right, we have the requirement to take a immunocompetent self-tolerant cell and expose it one time to a particular pathogen, to a particular antigen, before we can have anything happen. So there's this lengthy lead up, this fairly elaborate process, even getting us to the point where we can start to think about having a reaction. And then once we actually have that reaction, there's another lengthy stage in there where we divide, we make lots and lots of copies, and we circulate those copies around the body. It takes time, right? Now we can have memory cells that come in and kind of start us off halfway through the process and shorten it up for the next time round and get rid of the longest part of the pathway, but it still takes time. Okay, so at this point, we're ready to activate. So for our B cells, we have our naive B cell, and it has an antigen that's going to take it to a helper T cell. Okay. And this picture of it here now. I guess I took it out. Okay. Once this cross-linking happens, once these B cells and T cells talk back and forth between each other, what's going to happen is we're going to stimulate this B cell now to divide, to proliferate, to copy itself off. Okay. Most of these copies, right, these effector cells, we call these plasma cells. So the cell that's responsible for actually producing an antibody is called a plasma cell, derived from a naive B cell. And they make antibodies for a little while. Usually we talk about a lifespan of about 4 or 5 days, kind of at the outside for a plasma cell. And they make a lot of antibodies at a time, but again, it's only for a limited period. Those antibodies, however, often have a much longer shelf life. Okay, so those antibodies will be circulating in the blood for significantly longer than 4 or 5 days. They don't last forever, but they last a lot longer than the plasma cell itself does. The other option here, of course, is to become a memory cell instead. And these memory cells exist, again, for the second or the third or the fourth or however many times we're going to encounter the same pathogen down the line. And effectively, because we are starting in the middle of the process, we cut short a lot of the effort involved in having a response. We have essentially an immediate response the second time. So the first time, right, that we encounter a particular pathogen, we call this the primary response. Okay. Primary response requires that we bind to a receptor. We take that receptor to a T cell. We have cross communication between the two. We activate that B cell, and that B cell proliferates, divides. Most of these clones here become plasma cells that are making antibodies, these guys here. But some of them remain as memory cells. Right? So that the second time around, again, you have the response. Now, the thing with the primary response here, right, is that, again, there's a significant lag time. Right? We don't even begin to start on this process until at least 3 days, and sometimes as long as 6 days. Right? And once we start, we slowly ramp up. So even though we might start 3 days in, we're not going to have a noticeable or an effective response probably until 7, 8 days in. And again, we've talked about this. The idea here, right, of, the average illness you've got, you're usually feeling better in 7 days, right? So there are exceptions to this, right? But generally speaking, right, you're either on the mend or you're dead, right, within that period of time. And so this primary response really is kind of almost useless, right? You're not going to reach peak antibody levels until over a weekend, 10, 12 days in, at which point, you're back up, you're at work, you're at school again, right? It doesn't matter. So it's not great. But where we're going to shine, where we're really going to have a use for the adaptive immune system here is, again, if it's going to be something that you're going to expect to encounter 3, 4, 5 times in your life, right? 2 times in your life. Because that secondary exposure, that secondary immune response is going to be extremely powerful. Right? The first one was kind of a wash, but it was prep for the second. Right? Because we have memory cells, right, we don't have a lag time of days. We have a lag time of hours. Right? And start happening usually within 3 hours instead of 3 days. Okay? And we're going to pump out a shitload of antibody, right, really fast. So you're going to reach peak antibody levels within 2 or 3 days. And those antibody levels will remain high for a really long time, maybe up to a couple months. So where we're going to peak out at 10 days and begin to decline immediately with the primary response, we're going to have skyrocketing antibody levels for a long time. Okay? Antibodies themselves are actually more powerful. It's just a much, much bigger response. So if we take our primary response from before, right, and we tack it on to our secondary response, what we're doing is we're starting with these guys right here. Right? We're starting with an activated cell. We're starting with a cell that's already ready to go, and all it has to do is start dividing. Right? And so as we do this, not only are we going to have a faster response, but we're also going to find that we end up making more of these cells. Right? The sort of the cartoon representation here of having 7 here instead of 3 isn't just for show. It's we make more plasma cells. We divide more and more and more and more and more and more. And each of those plasma cells makes more and more and more and more antibody. And the antibody they make is more powerful. It's a much more it's a much higher affinity for the antigen than the previously released antibody. So it's more effective. We make more of it, and we make it faster. Right? And in doing so, right, we end up having a significantly increased overall immune response. So if we look at this in terms of timing, right, here in our blue line, we have exposure to a particular pathogen, in this case, pathogen A, we'll call it. Right? And our first exposure here is at day 0, right? And in terms of serum antibody levels, there's nothing, right? And nothing, and nothing, and nothing, and nothing. And not until day 5 or 6 here, we actually start to see some antibodies, right? And we have a response, right? We have a little response. And here by 10 or 12 days in, we have a peak level of antibody that immediately begins to decline. Right? By the end of the month, it's back essentially to 0. This is a pretty typical primary response. Now, the time of decline varies from pathogen to pathogen, so don't take that particular part as gospel, but the early timing here is pretty consistent. Right? Now, if at day 28, we get re-exposed to this pathogen again. So pathogen A again comes back into our life. We mount a immediate, within hours, a response, right? Make a lot of antibody a lot quicker, right? And if you look at the serum levels of antibody, significantly more, right, than we produced before. And we make a lot more antibody. And it declines relatively quickly, again, within 2 or 3 days. But that rate of decline is pretty low. So serum levels remain high for months afterward, right? Your body is saying, okay, obviously, this is something we're going to see a bunch. Let's just be prepped for it as long as we possibly can. Right? We're not going to play around. Right? We're going to deal with this as best we can. Now, if we imagine then at the same time that we got re-exposed to A, we also got exposed to a different pathogen, in this case pathogen B, right? While we have this rapid, powerful secondary response to A, we still have our same bullshit response to B because this is our first time seeing B. So again, we wait 6 or 7 days, right, before we have any response to B, and the response we have to B kind of sucks, right, and immediately kind of falls off. But the second time we'd be exposed to B, we'd have this powerful sort of secondary response. So again, the idea here, the first time's not very impressive, but the second, third, fourth times really does something for us. So when we talk about humoral immunity, then, right, the immunity provided to us by B cells, really what we're talking about here is circulating antibodies. The primary sort of crux, I guess, of humoral immunity. And humoral immunity comes in a couple of different forms, and there are multiple ways to acquire it. So one of the ways in which we can have humoral immunity is what we call active humoral immunity. And active humoral immunity is when your B cells are making antibody or capable of making antibody. They're yours, you can make them, we're all good. And you get this sort of active humoral immunity 2 ways. You've got sort of the old-fashioned way, right, where you get sick. You are directly exposed to a pathogen, you have an illness or some other kind of response to it, right? But you'll, at the same time, right, you prime the pump. You have memory B cells for the next time around. The other way that we can do this, and this is certainly the preferred way to do it, is through vaccination or inoculation, right? Where you are exposed to a dead or a attenuated, in some cases, for like the vast majority of vaccines are a dead virus or dead pathogen. In the case of, so if you get a nasal spray vaccine, for example, those have to be attenuated or weakened virus. So you can't get sick from a dead virus vaccine. Right? You might have an immune reaction. That's part of the normal circumstance, but you can't get sick from one. With a attenuated virus, like with a nasal spray, you can actually get the illness from it. It's not likely, but it's possible. But in either case, the idea is that you expose your immune system to the antigen in a low to no risk environment, right? So you kind of take that primary response, and instead of having to suffer through the illness the first time, you can start off with the secondary response if you actually get exposed to that pathogen later on. With something like the COVID-19 vaccines, those are mRNA vaccines. There's no virus in it at all. Okay, all it is actually the mRNA codes for the antigen, and so you expose your B cells to the antigen without having any part of the virus in you at all, which is pretty cool as far as those things go. They're also a lot safer, and they require significantly less testing, which is how they were able to get it done so quickly. And again, here, vaccines, they're really, really good. They're extremely useful. They've almost eradicated a number of really just horrific diseases. Um, there are essentially really no downsides to them. People that have reactions to them, a lot of them are developed in chicken eggs. So if you have an egg allergy, the dead virus ones are in chicken eggs typically. So if you have an egg allergy, you can have an allergic reaction to the carrier of the vaccine, not the vaccine itself. Or so the alternative then is, like I said, a lot of the nasal spray ones that are attenuated virus. You can get sick from an attenuated virus, but again, it's much better than getting sick the old-fashioned way. Um, your risk of that is pretty low. Never zero. There's never zero risk in anything, but it's pretty low. And obviously, of course, I hope I don't have to say this, but there is in fact no link between vaccines and any sort of neurological impairment or autism or any of that stuff. That study has been long discredited. The guy has been drummed out of the medical administration. He's lost his license, all kinds of stuff. So there is, despite what YouTube and internet celebrities will tell you, there's no link at all. The other way that we can get humoral immunity is what's called passive humoral immunity. And passive humoral immunity is when we get antibodies without making them. Okay, so one of these ways here, right? Well, I guess before we get into that, this sort of passive humoral immunity can be really, really good, right, in the short term. If you have a compromised or non-existent immune system, this is really the only way you're going to have any kind of defense at all against it. Again, like a vaccine or an inoculation, it allows us to cut short the primary response. Right? So if you get exposed to something, you leap right into the secondary response. But because you aren't actively making them, it's not a permanent thing. Right? Your protection is only going to last as long as the antibodies that you're given. Right? So it's not a long-term solution for us. There's no memory cells being produced here. And we acquire that one of two ways. Everybody acquires it when we're born from mom. Right? So, we've talked before about the idea that your immune system is non-existent when you hatch. Okay? The only thing really active there are the tonsils, and you begin immediately trying to use those tonsils to start acquiring some active immunity, right? But in order for you to not die in the process of doing that, you have to have some kind of level of protection. And so across the placental barrier, okay, you will get antibodies from mom that way. You will also continue to get antibodies from mom if you breastfeed. So again, two different ways that you're going to continually acquire ready-made, pre-made antibodies so that you can have this kind of buffer period between when you're born and when your own immune system starts to work, so that you don't just die from the first piece of dirt that you touch. The other way that we can do this, right, if that's the natural method of acquiring these things, the artificially acquired variant on this is something that we would give to, say, somebody that is significantly immunocompromised. We've tried this with some reasonable success for pretty far gone patients with COVID-19. Is to just basically just take somebody else's antibodies and give them to you. Again, it's kind of a stopgap solution, but if your body is incapable of mounting a response on its own, it might be one of the only ways to save you, which is kind of an important thing. And again, right, it's only going to last as long as those antibodies last. So if we want to think about this here in terms of what humoral immunity then looks like, again, talking about this flow chart, right? We have a couple of different ways of getting it, either through natural means or through artificial means, both in terms of active immunity, where you're making your own antibodies, okay, or in terms of this passive immunity, where you're getting antibodies from somebody else. Now, what we haven't talked about is what the hell an antibody actually is. What we're going to talk about here with antibodies, they're all going to belong to a group of proteins called immunoglobulins, or Ig. So whenever we see the term Ig, we're talking about an immunoglobulin of some description. And these are what plasma cells make. Right? They are basically a Y or a T-shaped protein with a couple of receptors on each end that attaches to a particular antigenic determinant. And like I said, there are multiple classes, each of which is going to be preceded by this prefix here, Ig, for, of course, for immunoglobulin. That monomer, and we'll see a cartoon of this in a minute, and I'm going to just, right off the bat, I'm going to warn you right now, I don't know why it is, but every year, unless I warn people, people don't think that they're going to have to know the structure of this stuff, and so they don't get it right in an exam. I'm just going to warn you that I am going to test you on this. Basically, the way that it looks is we've got 4 different chains, right, that collectively give us this sort of Y or T-shaped structure. Some of these chains are longer than others, and we call them heavy chains. Some of the chains are shorter than others, we call them light chains. And the important part here are the 2 variable regions. That's going to be the part that binds to a specific antigenic determinant. So when we talk about an antibody being specific to a determinant, that variable region is what makes that happen. The constant region is the part that is everything else. And so as we talk about AGG, AGM, AGI, or AGA rather, IgD, IgE, whatever immunoglobulin class that we've got, that is determined by the constant region. So we have classes of antibodies, variable regions for specific antigenic determinants. So, and we'll go through each of these and what they mean in a little bit. So don't worry about getting that right now. So the monomer, right, that's going to make up all of our antibodies in all forms, right, is going to look something like this. Right? So in this case, we've got sort of a Y-shaped kind of deal. This little hinge region in it. And we have a stem, right, that is just heavy chain, right, and the arms here above the stem have both heavy and light chains. You can see here that the light chains are short, right? Heavy chains are long. And it's at the end of each of these arms where we have the variable region. So all of this is constant. Variable regions out here at the ends. And this is where we actually are going to bind to the antigenic determinant, right, out here at these variable regions. Antibodies themselves, like I said, they come in 5 different flavors. IgM, this is one of the biggest groups of antibodies. It's a pentamer, so it is 5 of these things stuck together. And this is the first antibody that you make. So when you have a immune reaction, your plasma cells begin dumping out this IgM. Okay? And IgM is really, really good at agglutination. So again, when we talked about transfusion reactions in blood typing, what we were looking at with the blood typing, right, was whether we had a clumping or a clotting reaction with an antibody, right? That's what agglutination is. So IgM gathers these things together and clumps them or agglutinates them and kind of binds them in one place. IgA, right, is kind of a smaller version, right, of an antibody. It's a monomer, so it's just one of these, right? Or sometimes it's a dimer, which is 2 of these stuck together. And what it does is it is largely secreted in mucus. Okay? So when we talk about a mucous membrane, right, as a barrier, right, as a place where we're going to try to prevent entry of pathogens, IgA in that mucus is going to be a part of why that is an effective barrier for us. So in cartoon form, right, so here's our pentamer, right? So 1, 2, 3, 4, 5 of these monomers. All of the constant regions stuck together, all the variable regions facing outward. Right? Again, this is our IgM. This is our first antibody released. Here we have IgA in dimer form, so we have 2 constant regions stuck together. Their variable regions hanging out. Again, mostly this one here in mucus. There is some in your blood, but it's mostly a mucus antibody. IgD is a monomer, and IgD is actually the B cell receptor. So when we talked about maturation of B cells and the positive selection there on a B cell was whether they could produce a receptor or not. What we're really talking about there, and the reason I said it was an antibody, we're really talking about there is whether a B cell can produce IgD or not. And so that's the positive selection. IgG, excuse me, also a monomer, right? IgG is the antibody that we release after IgM. So IgM, we make it right away, we dump a whole bunch out, okay? And then later on in the response, we produce IgM. Okay. IgM is the only antibody we make in the secondary response, and it is also the one that we get from mom. So we're talking about having passive humoral immunity acquired naturally. This is how we get that. Okay, we get IgG from mom through the placenta. We get IgG from mom through her milk. And then finally, we have IgE. IgE is something that we have in response to allergic reactions. So when we talk about having a hapten, right? IgE is the R side of that hapten reaction. IgE we also release in response to parasite infections. So parasitic worms, things like that. IgE is there for that. We also have this as a part of an inflammatory response. So we go back and we talk to mast cells, we talk to basophils that are releasing histamine. IgE is responsible in part for the release of histamine from those things. And one of the important things to remember is that a B cell, an individual B cell, can make any of these at any time. Right? IgM, IgA, IgD, IgG, IgE, doesn't matter. Okay? The only restriction on the plasma cell, right, is that it can only make an antibody against a specific antigen. So it can make any antibody it wants to, but only against one specific antigen. And so, we see a classic example of this right away, right? We have to make IgD, right, first before we can do anything else. Cursor. There should go. Okay. We have to make this one first no matter what. Right? And then we make IgM, then we make IgG. Right? So we have to cycle through these at various points. And again, these last three here, B, G, and E, are all monomers, right? So they're only one of these groups together. As far as what we're doing, right, remember, we are opsonizing. An antibody does not destroy anything. It just opsonizes. Right? It marks something off to be destroyed. Now, that's not to say that we can't have additional actions, right? Things that are going to hinder or otherwise limit the ability of a particular pathogen until it can be destroyed. But the primary action here is to opsonize. Other things that we can do here, right, our neutralization and agglutination. We've talked about these two a little bit already, and these are really big ones. We can also precipitate. We'll talk more about what this means in a minute. And of course, you can have the classical pathway, right, of complement here by opsonization from an antibody. So neutralization is pretty simple. It's not particularly complicated by any stretch of imagination. Basically, what we're doing is we are simply, when we attach to a pathogen, we attach in such a way that we block the active site. We block a receptor on the pathogen, we block a receptor on the virally infected cell, and whatever else. And by doing that, we don't destroy it, we just simply prevent it from doing so. Simple as that. Second big thing here, the last thing we'll talk about today, is agglutination, and that's what we've talked about already with blood type. Right? We are clumping all of these things together, we're getting them all into one spot. A couple of things that we're doing with this, we prevent them from traveling, which is a big thing. We prevent them from spreading in the body so they can't go wherever they want to. But by bringing them all into one place, we also make it easier, right, to get rid of them. Right? When you're sweeping the floor, you don't make one little sweep of your broom into the dustpan and then move a little bit and do it again. You sweep everything into one spot and then you sweep it into the dustpan. Same thing here with agglutination. Right? You bring all of these things that need to be destroyed into one space so that phagocytes only have to go to one spot. And they can take care of all the garbage in one fell swoop. Okay? Wednesday, we'll come back, we'll talk about precipitation, we'll talk about kind of the rest of the immune system, we'll close it off at that point. One thing I wanted to mention, actually, before I let you go, I did check on it because I was trying to remember when the next lab exam is. The next lab exam is next week. So this week's lab will be the last content for that. So again, just kind of keep that in mind as you're preparing for exams and things like that. But that is coming up. Okay? All right. I will see you all later. Have a good afternoon.